So now let's talk about psychrometric chart. So now we will discuss about psychrometric chart. Psychrometric chart. So I will first define what is the psychrometric chart and how it will be useful. The psychrometric chart is a graphical plot with specific humidity and partial pressure of water vapor as ordinates and dry bulb temperature as abscissa. So I can write here the psychrometric chart is a graphical plot with specific humidity with specific humidity and partial pressure and partial pressure of water vapor as ordinates as ordinates and dry bulb temperature and dry bulb temperature and dry bulb temperature as abscissa. So now in the chart on y-axis you will find specific humidity and partial pressure of water vapor, and on x-axis you will find the dry bulb temperature. And in that chart the parameters are volume of the mixture, wet bulb temperature, relative humidity and enthalpy. So we can say that the volume of the mixture that is in meter cube by kg of dry air, wet bulb temperature, relative humidity and enthalpy of the mixture appears as parameters. So now I will draw the psychrometric chart and then we will see the different parameters. So I am now drawing the psychrometric chart here. So in the chart I am showing some curves here. Here we are having PW, that is partial pressure of water vapor in bar. Here I am having specific humidity that is on y-axis W, and on x-axis we are having dry bulb temperature. So now I will define some of the other things. I will define constant volume lines, constant enthalpy lines and wet bulb temperature lines. So here first of all I am draw the constant relative humidity line. So the constant relative humidity lines I am drawing here. These lines are constant relative humidity lines. So I can write these lines are constant relative humidity. That is, you can write constant relative humidity lines. And here the outer lines, that is phi equals to 100%, that is saturation line. Now I will draw the constant enthalpy lines. So I am drawing the constant enthalpy line. So similarly, I can draw the constant wet bulb lines. So here, this one, we are drawing the constant enthalpy lines. So H equals to C, H equals to C. Constant wet bulb lines also the same thing, that is wet bulb temperature. So by this way, in practically we can say that the wet bulb temperature lines are constant enthalpy lines. So we can say that enthalpy of the mixture remain constant during adiabatic saturation process. Because remember one thing I told, in adiabatic saturation process, the adiabatic saturation temperature, practically we are calling it wet bulb temperature. So here the wet bulb temperature lines and the constant enthalpy lines are same. So I can say that practically the enthalpy of the mixture remain constant during adiabatic saturation process. So it's a very important fact here. So I can write enthalpy of mixture remains constant during an adiabatic saturation process. During an adiabatic adiabatic saturation process. Saturation process. So now on this diagram I will define the constant volume lines. So the constant volume lines I am going to define here. These are the constant volume lines. So the constant volume lines. So basically it's just tilted lines. So these are the constant volume lines. It's not a perpendicular basically. It's a slightly tilted lines. So these are the constant volume lines. So now it's a clear representation of psychrometric chart. And now in the separate diagram I will talk about how we can find out wet bulb and dew bulb temperature. And the psychrometric chart here. So this one is the psychrometric chart here. So in that things I will just represent the constant relative humidity lines first. It is constant relative humidity lines. Now we can say that it's a constant phi lines. Constant phi lines. Now I will represent the constant volume lines once again, because in the previous diagram it was not clear. So the constant volume lines are like that. So these are the constant volume lines. So now suppose I am here at point 1. So at point 1, now we have to find out the dry bulb temperature. So first of all I will write here that is PW. I will write here that is W, specific humidity. I will write here that is dry bulb temperature. So now I know my stage is 1 and we are interested in dry bulb temperature, wet bulb temperature and dew point temperature. So these are some, suppose this is a constant volume line. This V equals to C here, constant volume line. So we are now at 1, so we have to find out dry bulb temperature. So directly we can find out the dry bulb temperature lines, that is dry bulb temperature, dry bulb. So because we are on the dry bulb temperature axis, so directly we can find dry bulb. Now we have to find out the wet bulb temperature and dew point temperature. So for finding out dew point temperature, what we have to do, we have to go parallel to x-axis towards phi equals to 100% line. So I am going parallel to dry bulb temperature towards phi equals to 100%, and now I am here at point suppose 1 dash. So now if I read the temperature on dry bulb temperature axis, it will be dew point temperature. So now we can easily get dew point temperature. So for obtaining dew point temperature, what we have to do, we have to move parallelly along the x-axis or parallelly along the axis of dry bulb temperature, and the point where the line will intersect with phi equals to 100% means relative humidity 100%. That point we have to read the reading on the dry bulb temperature axis. It's the dew point temperature. Now we have to find out wet bulb temperature. So wet bulb temperature, we have to go along constant wet bulb line. So at point 1, I will draw the constant wet bulb line. So this one is the constant wet bulb line, or we can say that constant enthalpy line. So I will write constant wet bulb line. Wet bulb temperature is constant. So now we have to move along this line. So now we are coming at one double dash, and at one double dash, if we see on dry bulb temperature axis, we are having a point here that is called wet bulb temperature. So now we can easily find dew point temperature, dry bulb temperature, and wet bulb temperature on dry bulb temperature axis. So now how we can find out the dew point and wet bulb temperature on psychrometric chart? It is very clear, and from this diagram we can write the highest temperature will be dry bulb temperature, then wet bulb temperature, then the lowest temperature will be dew point temperature. So remember one thing, the dry bulb temperature is greater than wet bulb temperature is greater than dew point temperature. So now tell me one thing, yeah, so now tell me one thing, where the dry bulb temperature and wet bulb temperature and dew point temperature will same. Suppose if we are on phi equals to 100%, then dew point, wet bulb and dry bulb temperature will be same. So we can write, so it's an important fact. I'm writing important fact here. At phi equals to 100% means for saturated air, T dry bulb temperature equals to wet bulb temperature equals to dew point temperature. Discuss about different kinds of psychrometrics processes. So now I will discuss about different kinds of psychrometric processes. So now let's start with first process, that is sensible heating. So for A, or I will define two process simultaneously, sensible heating. So sensible heating, or one more process we can define simultaneously, that is sensible cooling and sensible cooling. So first of all, I will draw this sensible heating and cooling on psychrometric chart. So this one is the psychrometric chart here. Here we are having PW. Here we are having specific humidity. Here we are having dry bulb temperature. So whenever there is a sensible heating or sensible cooling, the humidity will be constant. That is, a specific humidity will be constant. So now I will draw, suppose my point here, that is 1. So now 1 to 2, that is sensible heating, because dry bulb temperature here is increasing, and 1 to 2 dash, it is sensible cooling because temperature is decreasing. So I can write here 1 to 2, that is sensible heating, and 1 to 2 dash, it is sensible cooling. So on psychrometry chart, it is very clear, during sensible heating the temperature is increasing, and during sensible cooling the temperature is decreasing, and in both the process W will remain constant. So I will give the during sensible heating and cooling, what will be the heat load. So for heat load, I will give one formula for calculating heat load here. So for sensible heating and cooling, we are having Q12, we can say, that is G 1.005 plus 1.88 W T2 minus T1. That is for sensible heating. Similarly, the same kind of formula we can use for sensible cooling also. So remember one thing, Q12, that is for sensible heating, it will be G bracket 1.005 plus 1.88 W T2 minus T1. Now let's define the other problem, that is cooling and dehumidification. Cooling and dehumidification. Dehumidification. So basically this kind of process where we want cooling and we want dehumidification, the general application for this kind of process is summer air conditioning. Summer air conditioning. So summer air conditioning, in which we will get cooling and dehumidification. So first of all, I will draw the diagram or draw the process on psychrometry chart. So we know this one is the psychrometry chart. Here we are having PW, here we are having W, here we are having tri-bulb temperature. So in that process, we want to reduce humidity and we want to reduce tri-bulb temperature. So suppose we are here at point 1, and if we go like that, 1 to 2. So in 1 to 2, what is happening? The humidity is decreasing as well as the dry bulb temperature is decreasing. So 1 to 2, we can say that it's a cooling plus dehumidification. Dehumidification. And for this process, we can easily calculate the heat load. So I will calculate Q12, that is heat load for this thing. It will come G into H1 minus H2 minus of W1 minus W2 HF2. So here I will mention the H1 and H2, we know that is enthalpy of mixture at 1 and 2 point. G is the mass of dry air and W is the specific humidity. HF2, I will define the HF2 here. HF2, it's the enthalpy of water. It is enthalpy of water at temperature at temperature T2. So now with the help of this formula we can easily calculate the heat load. So that is generally for heat load. Now let's take another process, that is heating and humidification. Heating and humidification. Humidification. So I will give the example of heating and humidification. The process where we want heating as well as humidification, that is the process which occurs in winter air conditioning. So winter air conditioning is the best example for heating and humidification. Winter air conditioning. So first of all, on psychrometric chart, I will draw the process. So this one is the psychrometric chart. Here we are having TW. Here we are having specific humidity. Here we are having dry bulb temperature. And this curves we are having. So in heating and humidification, we will increase humidity, we will increase dry bulb temperature. So suppose we are here at point 1, and if we go like that 2, so from 1 to 2, humidity is increasing and temperature is also increasing. So I can write 1 to 2, it's nothing but heating plus humidification. Humidification. So now for heating and humidification also we can write the formula for heat load. For heat load I will write Q12, that is G H2 minus H1 minus W2 minus W1 into HF. By this formula we can easily calculate the heat load. Consider the another process, that is adiabatic mixing of two streams. That is adiabatic mixing of two streams. Two streams. So first of all, I will draw the diagram for adiabatic mixing of two streams. This one is one stream, and suppose this one is the second stream, and now it is mixing, and we are having this three. That is suppose 1, here 2 and this 3. For 1 we are having G1, W1, H1. For 2 we are having G2, W2, H2. For 3 we are having G3, H3, W3. So for mixing I can write G1 plus G2 equals to G3. So now I will draw this process on psychrometric chart. This one is the psychrometric chart here, and these are the curve. Here we know it is PW, here we are having W, and here I am having dry temperature. So now I will represent the different things here. That is 1, here 2, and this one is 3. So now we are having these things. So now I will say so W1, W3, W2. Similarly, I can say it's T1, it's T3, it's T2. So for adiabatic mixing of two streams, we are having a formula, that is G1 by G2 plus 2 H3 minus H2 divided by H1 minus H3 plus 2 W3 minus W2 divided by W1 minus W. So remember these two formulas for adiabatic mixing, that is G1 plus G2 equals to G3, and G1 by G2 equals to H3 minus H2 by H1 minus H3 equals to W3 minus W2 by W1 minus W3. About other process, that is chemical dehumidification. Chemical dehumidification. So now I will talk about chemical dehumidification. Some substance like silica gel, some substance substance like silica gel, that is product of fused sodium silicate, sodium silicate and sulfuric acid and and activated alumina have a great affinity with with water vapor. So they are called absorbents. They are called absorbents. When air passes through when air passes through passes through a bed of silica gel silica gel water vapor water molecules get get absorbed on its surface. Latent heat of condensation is released. Latent heat of condensation is released is released, so the dry bulb temperature of air increases. So now let's draw this process on psychrometry chart. So I am just drawing the psychrometry chart here, that is PW, that is W, that is dry bulb temperature, and this one is the psychrometry chart, and here I am representing the process 1 to 2. So 1 to 2, the temperature is increasing because the latent heat of condensation is released during this chemical dehumidification process, and humidity is decreasing. So we can say that 1 to 2 is chemical dehumidification. So now let's take another process, that is adiabatic evaporative cooling. Adiabatic evaporative cooling. So for adiabatic evaporative cooling, I am just drawing the process on psychrometry chart here first. So this one is the psychrometry chart. Similarly here PW, W, and we are having dry bulb temperature. So 1 to 2, this 1 to 2 process here, it is called adiabatic evaporative cooling. So this one is adiabatic evaporative cooling. So I can write 1 to 2, that is adiabatic evaporative cooling. So for adiabatic evaporative cooling, we are having H1 minus W1 HF plus to H2 minus W2 HF. So remember this thing, H1 minus W1 HF equals to H2 minus W2 HF. About the alternative method for calculating enthalpy for air water vapor mixture. So I am writing enthalpy of air vapor mixture. So here we know that is H equals to HA plus W HW, and here H is the enthalpy of the the mixture per kg of dry air per kg of dry air. So this one is the formula for enthalpy, and sometimes we can directly calculate the enthalpy by the following formulas. So for HA we can write CPT equals to 1.005 kilojoule per kg Kelvin multiplied with temperature. For HW I can write 2500.9 plus 1.88 T. So these two formulas are very important in calculating HA, that is CPT, and HW, that is 2500.9 plus 1.88 T. If you plug HA, HW value here, we can easily get enthalpy of air. But remember one thing, here we have to take T in degree centigrade. So I will write, so remember, take T in degree centigrade. So this is also important. For using this formula, we have to take T in degree centigrade. So by this way, we can easily calculate enthalpy of air vapor mixture.